The topic of today is the first of 3 lectures on foundations of machine learning. It's an introduction. And again, to just draw your attention back to the schedule, each one of these lectures will follow by essentially a set of examples from applications in heliophysics. So hopefully these lectures will set the tone in terms of the conceptual foundations, and then you'll see a set of very interesting examples that are directly relevant to some of the science that we've talked about in this school. So I want to start by talking about discriminative models, and of course I will talk in more detail about what that implies. Okay, yes, it is moving. This is also a little slow Saturday morning. Okay, so what I want to do is I want to talk a little bit about an introduction to the topic of classification and pattern recognition, because that's really at the basis of what machine learning tries to accomplish. And the progression is I'll start with something that's familiar to you from yesterday's lecture. So I'll go a little bit fast on the topic of linear regression, but I want to talk about that in the context of classification as a task, as opposed to estimation. Then I'll talk about logistic regression, which is essentially a change in that underlying model, probabilistic model, for the specific task of classification. I'll generalize that to what's known as support vector machine. And I'll talk about the multi-class regression and support vector machines. We start with binary classifications, we go to multi-class. And then my goal is to essentially show you that deep learning and various renditions of it, the architectures, are essentially the most general form of everything else that I've talked about. All of the previous cases are special cases of being able to essentially work and develop a nonlinear model. I've listed one text. Of course, there are hundreds of texts on this topic. There are many good ones. The one that I listed emphasizes a probabilistic perspective. Let me start with a bit of history. And of course, there is a rich history, and I'm only sampling on some. The history that relates to some of the concepts that have evolved in the last 2 decades really goes back to some research on neurology that showed brain as an electrical network of neurons. Cybernetics, which is a term that was coined by Norbert Wiener, described control and stability in electrical networks. I already alluded to one of those concepts in an adaptive filtering that Wiener came up with in the 40s and 50s. Of course, information theory has been very influential due to Claude Shannon and others, which really set the basis for a mathematical theory of communication, transmission of signals. Theory of computation by Alan Turing, which described digital nature of computation. Electronic brain, neural net by Walter Pitts and Warren McCloud. So let me show you an interesting piece of history. This is a proposal, essentially. You can think of an abstract to a proposal by Marvin Minsky in 1955 for a school. This one is an 8-week school, similar to some of the proposals that perhaps you received, Lika, for these kinds of focused schools. But I want to show you briefly, this was a school that was proposed to take place at Dartmouth, but it says the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described and that a machine can be made to simulate it. Yeah, how precisely it articulates exactly what happened. Yes. That's right. That's 70 years ago. Or is that right? Yeah. Okay. Or more, 80 years ago. Yeah, 45 and 25. Yes. So an attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. So those are the concepts. So I've listed from that workshop a list of the topics that actually came out. automatic computers, programming a computer with language. This is 1955, to remind you. Neuron nets, theory on complexity of calculation, self-improvement, abstractions, randomness, and creativity. Incidentally, just a side story, Marvin Minsky was active into late 90s. When I started grad school, I used to take the green line, the C line, you know that, Nick, from Brookline to Boston. And in the mornings, many mornings, I would run into him. And I would have conversations about my research. And he was very generous in offering. At the time, I was working on automatic sound recognition. And of course, you know, he was an authority on that topic. And so it was very nice to have to run into these types of people during your metro ride to school. Okay, so some familiar impacts of what we have seen. So in terms of pattern recognition AI that have showed up recently. So many of you remember that the chess is very important for essentially establishing the ability, the general ability of an AI system. In 1996, where Deep Blue at IBM played, but for the first time beat a chess master, world master, Kasparov. And a rematch in 1997, again, the same thing happened. And so it received a lot of press and public attention. Of course, many of you remember Watson from Jeopardy, also an IBM system. DeepMind in 2015, in terms in the context of games, both 15 and 16, Game of Go. Of course, autonomous driving, generative pre-trained transformer, GPT, we all know that, by OpenAI in 2022. The most recent version of that just was released about 2 weeks ago, GPT-5, and some of you, I know some of you have experience with that and I think are impressed. This is essentially the subject of the topic for generative AI, is the topic of tomorrow's lecture. Okay. I want to talk about something that has some implications for scientific applications, and that's DeepMind's latest weather prediction model, which now is more than a year old, maybe 2 years old, GenCast, which outperforms traditional physics-based models and even other AI models in terms of accuracy and speed. So why is this consequential? There was a time when I spent time inside the Beltway in Washington, D.C., and there was a lot of discussions about maybe ideas for example, prediction, space weather prediction. And as people are writing ideas, there was a lot of emphasis on making sure that they would put in front of any activity, whether it was modeling, simulation, everything, physics-based in front of it, okay? And of course, the idea is that it's important to understand the underlying physics, but the objective was to improve prediction. And every time people brought up the idea that perhaps, maybe if you keep the objective in mind clearly and you just want to improve prediction, maybe with sufficient data, it is possible not to just emphasize one particular approach based on physics to do that task. Maybe data can speak to us. And of course, it took almost a decade and a half for that illustration, but this is impressive. The fact that such systems can outperform all of the difficult governing equations that can put in a model. Okay, so this is an example of, in my opinion, showing the power of data. If you have enough data, if you have good data, and if you have the clever ways of utilizing. Okay, so let me set up the problem. I'm going to show it in the context of cats and dogs. So, of course, you can replace that with flares, coronal features, whatever it is that you want. But basically, what I want to show you is the idea behind why it is that we are able to perform the task of learning in an automated fashion. So the idea is that you have images in this case, and you have an algorithm or a model, and you want to ask the question, is there a cat in an image? Of course, for us, for the human perception, it's easy to do, okay? And so what is the formulation of this problem? The problem is that you have an input data. Let's denote that by x sub I, x being the data. It can be a vector. It can be an n-dimensional vector that essentially represents any data point in an n-dimensional space, because that vector represents, essentially you have the magnitude and the location of that point. And you have a labeled output data. I'm talking about the label in this context first, meaning that somebody has already gone through a set of images and said, yes, there is a cat in that, or there isn't. Somebody has decided that ahead of time, okay? So then there's an input. So you have these data, X of I's, and the output Y of I. And then in the middle, we have a model or algorithm. And of course, what we want to do here is what's referred to as inference or prediction. What that means is that you have new data, X of I plus 1, that hasn't been seen before that comes in, and you want to find out which class does it belong to. In the context of this simple example, a binary classification, you want to be able to automatically say, is there a cat in the image or not? Okay, so what is the learning? The learning part is that the model algorithm depends on a set of parameters, and this is essential. This is going to be a theme for the remainder of today, which means that we have these parameters. We parameterize that, essentially the algorithm, the thing in the center, and we talk about the learning, which is just the fitting of these parameters. So this relationship, this internal relationship, it's parameterized. Of course, we'll talk about how that's parameterized. But then we want to fit those parameters. Let's call them W. And based on data set, this D is a set of pairs, Xi's and Yi's. So in the simple example that we have, how could we recognize a cat in that algorithm? So what should the algorithm be? In the context of images, you can just look at a pixel. Pixel may have a grayscale value. You can vectorize that image and essentially turn it into that data vector, okay? So given that we know how a computer sees an image, how can we recognize it? I want to emphasize the difficulty of being able to just write an algorithm to recognize a cat. Why? Because you look at those pixels, maybe, how do you define in an algorithm, in a computer algorithm, if you want to identify an object, how do you write an abstracted notion of a cat? Different sizes, different shapes, different. So that's the difference between something that human brain is capable of generalizing, abstracting that concept and recognizing a cat most of the time. But it's not easy to just convert that directly to a specific algorithm. So that's where the learning aspect comes about. So very hard to describe what the cat looks like to a computer. However, we can look at a whole bunch of databases, and that's what human perception does, but can we mimic that in the context of a computer? So the idea here is that you have thousands of examples, and somebody, this is what I mean by the supervised aspect of the learning, somebody goes there and probably marks that each one of those images. The whites say, yes, yes, there is a cat. The black means, no, there is no cats. So somebody labels the data, okay? Ahead of time, you have these XY pairs that you know that have been already trained, essentially labeled, and you can use it. Okay, so if we have that, and if somebody actually puts that there, it's very easy for a computer in this case to say that, well, if the bottom left corner is black, 0, say no, otherwise say yes, and that's an easy task to do, okay? Except that we designed this very simple classifier that works on this data set, but doesn't work on real data, okay? And here is what I want to emphasize. Really, the essence of machine learning is that it has shown that there are mechanisms to search for mappings which generalize. Generalize is the key word, because it has also statistical notions of a distribution generalizing to perhaps changes, shifts in that distribution. Generalize implies that now you have other new data that may not have been in the training data. That's really the essence of it. And a lot of times, for people who have not really thought through or have experience with these, it's hard to imagine that you train, you have a training, but then you look for things that are not in your training data. How is it possible that you generalize it? Everything should be, all of the information should be captured in that training data. So the scope of what I'm going to talk about today is to just show you the conceptual building blocks, but I will not talk about generalization, which is a very, I would say, deep topic and a difficult topic. It's a subject of statistics and computation and applied mathematics, on which there are books and courses taught, but that's beyond the scope of what we're going to talk about today. Okay, so let me categorize the machine learning algorithm, pattern recognition algorithm. So available annotated data. If you have annotated data, like the example that I gave you, call that either, if it's annotated, if you have access to annotated data, it's supervised versus unsupervised. Complexity of model. linear versus nonlinear. And that's exactly what I'm going to do today. I'm going to start with linear and then end at the most general nonlinear model that's captured by neural networks, a layered perceptron, multi-layered perceptron. So the structure of output, that's another way you can categorize these types of problems. For example, what do I mean by structure of the output? If you're talking about classification and there are multiple classes, you may want to just essentially, if it's do the prediction or classification for individually, you run your algorithm on for each class. Is there a flare? Not a flare. But there are things that, for example, for human, some information, a new human subject comes, and you say, is this person taller than this or not taller than this? Weight is larger than this or not larger than this? But there's correlation between some of those classes. And so to take advantage of those correlations is what's referred to as structured learning, as opposed to just independently running your prediction algorithm on each one of those. And of course, modeling of data. If we only have the XI, we don't have labeled data, that becomes a subject of generative learning, which is a subject of tomorrow's lecture. And if we have XY pairs labeled data, that's the subject of today, which we're referring to as discriminative learning. Okay, so what are the main components? An input called observation or data point, we denote it by X, a discrete output. Because the number of classes, we're talking about classification, of course, we're going to increase that number, but it's a discrete set. We denote that by Y. They're also called label or class, and a decision function that sometimes is called classification rule. So it's a Y is f of X. X comes in, and you have to decide which one of those classes in that set output space Y we have. Okay. So, and the problem is to construct that decision rule for us. Okay, so I'm going to start with the most straightforward, which is the connection to yesterday's lecture. And I'm going to go rather fast on this because we've already seen some of these topics yesterday. Okay, but what's the idea? Just very quickly on the notation, we have a vector and dimensional vector. We have a matrix, which is essentially a set of the input data. We define the norm in the standard Euclidean norm. Which in 2 dimensions, essentially, it's just the distance or the length of the vector. And the rest is just notations, straightforward notations in linear algebra. I'm not going to talk about the probability. It's just the notation. We have used this notation already, the notion of expectations and discrete probability distributions or probability mass functions, which I'm going to use. Okay. Then, of course, a few concepts. We can define mean variance. Again, I will skip all of that, but just as a reminder, this is what we worked with last time. We spent quite a bit of time talking about this multivariate Gaussian, which becomes important, okay, and the covariance matrix. And a few operations, again, I've just listed them there, but operations on essentially on multivariate functions, computing derivatives, and I'll just leave this here as a reference for you. But what is the problem of linear regression? So you have, this is the example that I was illustrating yesterday with my hands, but now you have the figures. You have a scatter plot. And in the simplest case, in this 2-dimensional example, what you want to do is you want to fit a function to that. And let's start with the simplest function, which is a line. Okay. So then for a line, of course, we all know you have the 2 parameters. In this case, that vector W has 2 parameters, W1, the intercept, and W2, the slope of the line. And we are given a set of pairs, X1, X2s, and we want to find the parameters W1 and W2. And of course, as we have seen, remember yesterday with least squares, essentially the idea is to minimize the error or the projection of that error into the smallest length vector, which essentially implies, in this case, in the Euclidean space, you just minimize the sum of the errors from each point as projected on to that line. In other words, in this picture, you add up all of this, the magnitude of these green lines, you add them up and you try to find, then you move your line, you change W1 and W2 until the sum of all those green lines is the smallest. That's essentially the task, right? Okay, so how do we write it? We write it in vector notation. You have the y's, you have the x's, you have W1, W2. And this notation, again, argmin means the argument that minimizes the expression as opposed to the minimum itself with respect to the two parameters we are fitting, W1 and W2. And of course, you can write it in a shorter notation. This is our cost. This is the minimization problem. And in this case, again, as a reminder, we did this yesterday because it's a simple problem. We can compute derivatives. We can actually analytically find a solution for that. And the simple solution, all it takes is just write the expression inside the norm, transpose, times that expression. And then you have 4-term, multiply it through. And there are 3 terms that are functions of W. And then you just basically just compute the derivatives of these vectors and work out the algebra. And this is essentially what we come up with, which is the form that we saw before, okay? The set of normal equations. Okay, and so that's an example of what you're seeing. And the part that, again, many of you have experience with, but I just want to write it in this same notation, is higher dimensional problems. Now, generalize that to higher dimensions. And we want to talk about, for example, higher order polynomials. In general, it doesn't have to be just a line. It can be any function, any analytical function that makes sense, of course, can be a fit, or even not a function directly. It could be a feature of the set of inputs, okay? So here's an example of where, for example, we can have higher orders, not just the 2-dimensional omega W0, W1, but maybe K of them. And the only reason I'm doing this is just to show you, without really dwelling on it, is that it's the same exact framework works with just a slight change of notation. You just keep the notation the same. And let's see. Yeah, so all you do is just the dimensions change a little bit, okay? But nonetheless, you end up with the same type of regression problem, okay? Here's an example that when you go to higher dimensions, you have a fit. But the question that I have for you, and the question is related to what we talked about yesterday. What if n is less than d plus 1? As a reminder, what I'm saying is, what if I have more degrees of freedom than constraints? What do we do in that case? So it's an underdetermined situation, right? A regularization, exactly. So, I mean, basically, you have to pick a solution. You may be in the regime where you have infinitely many solutions. You can pick a minimum norm, but if you have the issue of noise, you may want to regularize the problem, and we talked about that yesterday. Okay, so the idea, again, was just in words. We want to make sure that the parameters are not too large. Maybe we pick the solution that has smallest energy, or the minimum norm solution. And we want to make sure that we can invert the matrix. And this is an example of a very simple form of regularization. A quadratic cost side constraint, what in statistics is referred to as ridge regression, okay? And of course, the question came up, and what we will see in the subsequent lectures is, can we do something more sophisticated about these types of constraints? And in particular, is it possible to have physics-informed constraints to essentially tackle a problem that does not have an easy solution, as we saw yesterday? Okay, the simple form of this ridge regression, all it does is that, this is something we saw yesterday, it just replaces the original problem that perhaps XX transpose didn't exist with another term that essentially scales the diagonal elements of that original X transpose matrix, so that it becomes better conditioned, and perhaps a better inverse can be found for it. That's essentially the effect of that here. Okay, so one more variation on that theme, higher order polynomials. So clearly, all we have to do is to just basically, we have W2 xi squared. So essentially now you're seeing that it's not x itself, but a function of x that we can have. And the point that I want to emphasize, without going through the details, is that the same exact framework allows us to generalize this problem to, for example, polynomials, higher order polynomials. Again, we have this new matrix, capital Phi, that has dimensions n by m, and we have the corresponding m of these elements in the weight vector the parameter vector W. And the solution, if you go through it, you would not be surprised that it has the exact same form, but except that instead of x, now you have this function of x, okay? And so that should give you an idea of the fact that a lot of times you don't need to work with the data directly, but you can work with functions of your data, and that's what's known in machine learning as features. Okay, I want to ask you something here. This is what I can tell you is that you see the red line, that's a fit to a line, and then you have the function, that the one in black, that essentially uses a, maybe, I forget, 10th degree, maybe higher order degree polynomial. Which one is better? Okay, most people prefer red, so let's do a binary classification. How many people prefer red? Okay, most people prefer red. That's good. Well, what's wrong? What's the problem with the black line? Overfitting. Okay, so it's overfitting, but I want to emphasize that, look, in the regions in the middle here, okay, where are we? In the regions in the middle here, it actually does a better job, right? It's just that it overshoots in those few points. And what does that mean? What that means is that, first of all, 2 points. First of all, a fit. When people show you a fit, you know, and doesn't matter where, take AGU for an example, always ask the question, what went into that fit before you just accept the results? That's the first point that I'd like to make. The second point is that depending on what went into it and depending on what you care about, one may be better than the other. So you really have to, that's another example of really understanding things under the hood so that you can really make sense of your data in a principled way. Okay, so generalizing everything that I talked about is that we can write things in the form of the relationship. You have y, now you have this function phi of xi's. Okay, so a function or a feature, set of features, and the same exact machinery works. Nothing changes, and that's good. But I want to talk a little bit about, so this is essentially the error. We can also talk about a probabilistic view, which we did yesterday. Again, I'm going to very briefly review it, but it's going to come up when I transition to logistic regression. So a probabilistic view is that you can think of this as x's, each one of them is modeled as a Gaussian in the first case that we have. This is essentially the standard Gaussian. Of course, in higher dimensions, this becomes multivariate. But how do we find W? We find that W, as I went through yesterday, we spent most of yesterday on this, with the background for today, is through essentially a function that is the conditional density, probability of the labels given the set of inputs as a function of parameters. You remember what the name for that function was? A likelihood, right? A likelihood function. Okay, so we have this likelihood function, and for example, a linear model, we saw that because of the linearity of Gaussian, essentially the likelihood means that we have the x's for the parameters, and the output y also becomes a Gaussian. That's why the likelihood takes on the form of a Gaussian, and that becomes our model. And I've just written it again in terms of this, instead of x itself, I've just written it specifically in terms of the product that we saw before, the weight times the feature, the function of the input x. And there is one concept that I have to emphasize, we did not talk about that, is that ultimately we want to be able to use these likelihoods because we want to be able to maximize them. We want to maximize those likelihoods for our regression problem, for our classification problem. In order for us to be able to do that, of course, in one-dimensional case, it's easy to talk about these probability functions, but when you go to higher dimensions, now you have these multi-dimensional density functions. And in general, they're a function of all of those dimensions, right? So you have to make certain assumptions to be able to reduce them to perhaps the product of those individual density functions, the distributions. And the assumption that's important is what's known as IID, or independent and identically distributed. And this is, again, in the context of central limit theorem, yesterday I said that you can draw samples, but they have to be from IID samples. Okay, that's the essence of the result of central limit theorem. So what does that give us? What that gives us is that now probability of D, remember D is high dimensional because it's pairs of xi's and xy's, x1, y1, x2, y2, and it goes to n dimensions, right? So it becomes an n-dimensional probability function distribution, but I can write it as the product of one-dimensional ones. This is the product of one-dimensional ones for each one of those data label pairs, okay? And that means if you just simplify this, you'll see that we have this form at the outside, and they can also write this in closed form because it's a product of all of those individual ones. And of course, I want to maximize this likelihood probability of D. That means that I can minimize essentially the inverse of that because of the negative in the exponent. 1/2 is just a constant to just keep the algebra simple. Okay, the next thing that I want to touch upon is to use linear regression for classification. Is linear regression a good algorithm for classification? Intuitively, what would you say? Depends on the data, yes. But what does linear regression do for us? Yes, you're saying no. Yes, so remember, how do we do classification? Let's start with, how do we do classification with regression? We do this fit in this example, and then we have a decision boundary here, for example. Anything, you can see all the x's that are to the left, we call them the class that's blue. To the right, we call them the class that's black, right? That's essentially what we do. But we have information everywhere along that line. Whatever data we get, and if the data is in this cluster, anything that's to the right of this line on 0, essentially we call it one thing, and then the other one and the other thing. But it's essentially an overkill, right? Because we have assumed that we have this line values everywhere, but if we know ahead of time that our problem is a binary classification, it probably may not be the appropriate model for that task. Furthermore, look what happens. If I get new data, so suppose that I get new data that belongs to this second class up here, okay? Now I'm using all of this data for my, essentially this label data for classification. That changes the weights of that vector, W1, W2, right? And that means that it changes the line. And when it changes the line, the decision boundary gets shifted over here, right? And that's to the right of 0, this line. And that means that the points over here, which originally were the correct points from here to the left, are now going to be labeled as blue, even though they're black. Okay, so the fact that we have these outliers, it just essentially messes up my classification problem. Okay, so why is this? We can look at essentially what you were talking about, this quadratic loss. So what I'm doing here is just writing the loss, and I'm going to plot it on the y-axis of yi and the product b of xi. So the simplest form is just x itself times the weights, basically just the product of that shows that line parameters. And I'm going to write it in this form, essentially 1/2 of yi. This is the least squares or the quadratic cost. And I can write it in a way that essentially, because yi, I can say that essentially it's a binary classification. So let's say it takes the values -1 and 1. I can just write it in a slightly different form so that I can get a sense of this 1 minus the product of either -1 or 1 times the term that I'm going to call it the function of xi and w parameters. And then the whole thing, that when I multiply it by y, I write this as a function of all 3 of those parameters: the data, the label, and the weights. Now, you may ask, well, why am I bothering to do this? And the reason why I'm doing this is I want to show you that by the end of today, this general function of these 3 parameters is exactly the way we parameterize a multi-layered perceptron. okay, a general function, and this is starting point of a specific case of that. Except that we have a little bit more complexity in terms of the form of the cost. And I'm going to show you that increased complexity, hopefully at a faster speed than I have been going so far. So this, if you plot that as the loss and the product of this function, essentially f, you'll see that the regression, linear regression, has this quadratic loss, okay? And as opposed to what we ideally want, which is this 1, 0 loss, we want to be able to call everything to the left. That corresponds, if we guess things correctly, we want to have no cost, so we want to be here. And if we guess cases incorrectly, which becomes either the label was 1, we guessed -1, or the label was -1 and we guessed 1, that product is negative. And so we want to give it, we want it to incur a cost of 1, and everywhere else is the regime where our prediction was the correct one. It was either -1, -1, or 1, 1. Okay, so that corresponds to these values, and that's the black is exactly the ideal form of the cost we want for a binary classification problem. But instead, this is what we have. What does it show? It shows that everything to the right of here, we are actually penalizing cases that are very easy to classify. Okay, so that's why logistic regression, linear regression is limited for this task. Okay, how to fix it? And that's the topic of logistic regression. And I talked about the probabilistic interpretation. And the idea behind logistic regression is that perhaps Gaussian is not a good model for the data if our task is a binary classification, 1 or -1, or 0 or 1. Okay, so what would be a better probabilistic model? The underlying distribution that corresponds to that is a Bernoulli distribution, right? Which is essentially it's a distribution. It's a discrete distribution. It has probability p for the case. It's like a flipping of a coin. If you get one, it's p, and the probability of the not getting heads, for example, it's 1 minus p. And of course, you can write, in addition to that, that expected value of that probability. And in addition to that, we pass that through a sigmoid function so that we can have this transition, the sharp transition, for essentially the cases where we have only two, a set that's a binary set of classes. Okay, so and then if I write the specific form of the probability mass function, which is the term for the discrete density function, or the density function, probability density function of a discrete data, discrete random variable, what you see is that probability of the class being equal to 1 given the data has this form of a sigmoid function, 1 over 1 plus exponential of negative omega t phi of x. Okay, that's the standard form based on the underlying assumption. And what's the probability of the class being -1, the other element in the class, the other element we would predict given x of I, given the data? It's just basically, because it's binary, Bernoulli, 1 minus the previous one. If you just go through the algebra, this becomes essentially just changes the sign inside. And so that means that now we have the two possible outcomes, and we can combine them taken together to write the density function, probability of y given x, which has this form, 1 over 1 plus exponential of minus y w transpose and phi of x. This is a form that's important for people who work in the area. They will always recognize that this is the form of a logistic regression. Okay, that's the model of a logistic regression. So what do we do with this model now? That's how we model the case. Well, clearly we want to do some sort of an optimization. We want to maximize the likelihood based on this model. And if you write the likelihood, it's essentially, I've just repeated that form here. That's the conditional probability, which is the likelihood. And then we're just going to play the same game. The sample data points, because this is only for one set of data points and labels, but we have a whole bunch of data points. So we write that as a product, invoking the assumption that each one of those data points is independent, and identically distributed. All of them are based on this underlying Bernoulli distribution. So by doing that, what can we do? We want to choose these W's to maximize this probability. So there is only one more step to be able to handle this, and that step is the following. We write this product, okay? And now we want to be able to essentially optimize it. And what we do is, first of all, I can change that probability, change the sign to negative and change the maximum to a minimum problem. But the next thing I can do is essentially I can take the log and convert, because of the log, convert the product to sum. Okay, so now I have a problem that's essentially linear, these sums. And I can invoke the log. Again, do you remember why I can, if I'm maximizing something, if I'm looking for optimum of function, why can I use the log of that function? What aspect of the log? Monotonic. It is a monotonic function. It doesn't change the optimum of the function. And if we combine them, this is the final form of logistic regression. So we are minimizing with respect to the parameters log of 1 plus exponential of that function f of the 3 elements. Okay, so that's the cost of logistic regression. What do we do with it? As a reminder, let me just show you the comparison. This is linear regression. This is logistic regression. And you can see that what the difference is, how we have changed the form of the cost. We have a log outside and an exponential inside. And of course, what is done in machine learning is to work with something known as the empirical risk minimization, which means that we have this data, this labeled data, the pair, and we want to minimize some difference. And that difference, by the way, can be many different things. For example, it could just be the quadratic distance between these yi's, the labels, and the function of xi and w. And that's the example that I showed you for linear regression. So what do we do? By the way, in terms of just visualizing it, remember, we had the 0-1 loss, which is the ideal thing, the quadratic loss from linear regression. And if you plot that and just go through the math, the simple math, just convincing yourself that this is what it looks like. This is logistic regression. So you can see that in areas where it's easy to make that essentially classification, it actually penalizes those areas less. Okay, so it's a better model for that task. This is a good time to ask the question that, well, why do I need to, if this is my goal, this black line, why do I need to settle for things that like that red line as a cost or the blue line? Why don't I just directly go for the ideal case where I have that cost? Right, but so what I'm plotting is, so again, new data comes in, but what I'm saying is that I can penalize the new data using a cost that looks like this or a cost that looks like this. In the first case, I have an analytical solution. In the second case, as we will see, I actually need to do that numerically, the search for that optimum. And that should really give you a hint as to why I cannot do the search. Like you said, we don't know why, we have to do a search, but a search for an optimum for a function that has this sharp discontinuity is not easy, right? So there are people who actually try to come up with ideas, with subgradient ideas in optimization, but it's not easy, and you don't get these straightforward good results. That's why you have these surrogate functions as your underlying models. So, okay, the final thing about logistic regression, how to optimize. Well, this is the minimization problem. We can take the gradient and set it to 0. You take the gradient of this function, you apply the chain rule. This is the form that you end up with, set it to 0, but we don't have an analytical solution. Okay? And so we have to do a numerical optimization, searching for the minimum in that function. And that's not a problem that you can do with straightforward optimization methods, the same ones that variations of that theme are what are used in multi-layered perceptron deep nets. And essentially you use something like gradient descent, which I briefly touched on yesterday. Okay, so what does that mean? That means you essentially, these are the steps. You initialize, you choose the step size or the learning rate, you compute the gradient, and you step in the direction of negative gradient, just like you would do coming down the steps, and then you iterate until you have some convergence. So, of course, there are more complex algorithms, but this works fine. Many of you can implement this in Python in about 20 lines, the logistic regression, or those of you who are very compact, even shorter than that. Okay. Okay. That's, yes. Yes. Yeah. So exactly. So yeah, let me elaborate on that. That's a good, no, that's a good clarifying question. So this is the cost, okay, for linear regression, but I need to find its minimum. Okay, I need to find its minimum because I get new data, and I need to same thing for in this case. I need to find where if I get a data. If I get data that is in some range, depending on the values of W, and the data is X. X is what we get. W are how we parameterize our X. And of course, Y is the different class, the choice of the class. And depending on where that data is and what sort of parameters I change, I end up in different places on that cost. Okay, that was a result of this. For example, the quadratic cost came because I defined in the least squares I want to minimize the error, the total error. That's the way I define it. Here, I'm saying that that's not what I want to minimize. It's a different cost because that makes more sense for my binary classification problem. And the point I was making earlier is that it is not easy for me to do that search and find the optimum of a function that has discontinuities, because you have to search, for different function values. That's basically what optimization is. Yeah, you change the value. You have an X, you change W, and you find exactly where that is. And then you have to find out where that minimum of the set of W's with your given data are in order to achieve that minimum. Does that make sense? Yeah. Good. Okay. So that's the algorithm. You can look at some examples. You have this, for example, a class where you have the data is binary in this fashion. And this is the form of that logistic regression, okay, the decision boundary. And you can also see that this is the steps in your gradient descent until you converge to the solution. You iterate. There was a discussion last time, what if you overshoot? So of course that can happen. Sometimes you may want to make that happen. There is a technique for sometimes wanting to do that for a stagnation in optimization known as momentum, right? So some of you may have experience with that. Okay, so you have this data loss, and this is the case where we have outliers, and you can show, basically what I'm showing is that this is robust to outliers, even though we have outliers here, unlike the case where we had a line that changed its slope. Now you're essentially fitting exactly to that model because you started with the correct model. Okay. All right, so briefly as comparison, we have for linear regression, we have closed form solution. We have a Gaussian probability model, but it's not too well suited for classification. For logistic regression, it is well suited for binary classification, and we can generalize it to multi-class. And we have an underlying logistic probability model with a Bernoulli prior, but there's no closed form solution, and we have to solve it numerically. Okay. I want to transition and generalize this a little bit to something known as support vector machine that were used for a long time, up to maybe 10, 15 years ago. until people realized that the generalization of this and or being able to capture nonlinear dependencies in your data and model can be performed if you have the resources computational and you have the data with multi-layered perceptrons or deep nets. And in fact, if I have time, I will show you that this is just a special case. This is related to both logistic regression and to deep nets, okay, as SVMs are. So what's the idea behind, again, there's a lot of detail that I'm going to skip over, but the important thing to keep in mind is that what is the conceptual idea behind it? The conceptual idea for a binary, let's start with a binary SVM, intuitively is that let's look at the simple, straightforward case where we have two classes and the clusters are such that there are some data points here and some data points here. So you can clearly separate those two classes in a linear fashion by a line that would separate those two. Of course, that's not always the case, and we're going to look at that, but let's start simple, okay? And if you can separate these two by a line, you can, through very simple math, show that the distance between those two lines is 2 over the norm of the weight, the W. So essentially, if the weight times the phi, or the features, is 1, you're going to declare this class. If the weights times those is -1, you're going to declare the second class. That's how you decide which class you're in. And what that means is that you want to essentially draw a line here, but this is what is known as margin, which is 2. This is the length of this vector with the arrows, 2 over norm of W. You want to maximize this margin. You want to maximize the difference between these two, okay? And you also want to find essentially a low energy minimum norm solution. So you want to minimize, you want to find the smallest weights, W, just like we did before. But you want the product of this Y times WT times phi to be greater than or equal to, it can be actually any number greater than 0 in order for you to say, to declare this class being the correct one or the other one, because as you can see here in this example, the product of these two, you call this to be declare this as the class, being -1 as at this side, but essentially you just write this in terms of an inequality, and for simplicity and for being able to relate it to other things we have talked about, you can pick this right-hand side, something known as a task loss. Generally, it's an L, but let's pick it as 1, okay? And the issue is that what if data is not linearly separable? What does that mean? What do I mean by that? I mean, what if I have in this case, not all of these crosses are on the left and all the circles on the right. What if I have a cross right here? I cannot draw a line, a boundary between those two in that case anymore, right? So how do I capture that in my model? I need to change this model that I just talked about, which is I have the inequality, I have the side constraint, but I need to change it a little bit. And the way you change it in SVM is by something known as slack variables. All that means is that I'm going to allow some deviation for some data points. If one data point in this one, this cross, instead of being there, shows to be in the other class, I'm going to define a length, and I'm going to call that slack variable, let's say C for that data point. And then I'm going to essentially allow this wiggle room for all of such data points that belong to the other class that prevent me from being able to draw a line, a boundary decision in a clear way. I'm going to add all of those to this side constraint. Okay, so the sum of all of such vectors. And now what do I have? I have such that, and this is my original, this cost, this condition now is going to correspond to essentially that drawing a line, but allowing for some of these slack variables. Okay, so that in case that I cannot draw a direct line. And so that's what changes. And so now you have that change, and then the question becomes, so again, as a reminder, we have this is the minimization problem subject to the condition that essentially captures the slack variables. The equivalent is I can write it as a minimum of the weights. I want the smallest weights. But notice that I can rewrite this condition essentially as what? As maximum of 0, 1 minus the term over here. Why? Because all I have to do is just basically take this C to the left, take this term to the right, it becomes 1 minus this term, okay? And we know that these are positive. So essentially, you can see that, and by the way, I want that total to be minimum. So by choosing a function of either max of 0 or 1 minus that term, it essentially gives me the same cost. All I have done is that I have rewritten the same exact model in this other form, okay? And of the empirical risk minimization, you can write it in this fashion. And the what's known in the case of binary SVM, which is known as hinge loss, corresponds to this magenta function. You can see that essentially it has this form in comparison with, for example, log loss, which corresponded to logistic regression. So those are, yes. Mm-hmm. Yes, you still have to, because the model is linear. You're going to draw a line. The question is, where do you draw the line? How much influence there is with samples that appear in the other class, okay? So you're deciding where that should be, that classification should be. And of course, the more outliers you have or samples that belong to the other class appear there, you still have to make a decision, but they play a role. They all play a role, but the way they play a role is essentially by allowing to appear in your optimization problem. I mean, if the data is not linearly separable, you can't change that. It's your data, right? So you still have to do something that makes sense in the context of your task. Yes. Yes, but not in the same way as before, because your cost is not the same quadratic cost. We have defined it in a slightly different way. In fact, this shows it. This is the cost, this magenta, right? So the amplification is not as severe. Okay, so how do we optimize it? The optimization is a little bit more involved, and we don't have time for that. But the reason why it's a little bit more involved is because it falls under the category of constrained optimization problems, meaning that now we have a minimization, and it's subject to a side constraint. Those of you who have taken a course on optimization theory would recognize that essentially you can use methods, for example, compute a Lagrangian or obtain the dual, and you can optimize it in the primal or in dual, but essentially you have to use some constraint optimization. Okay, so I'm not going to go over the details apart from telling you that you can optimize these things in a stable fashion. There are many such algorithms for performing this optimization task. Okay, so just to recap, we have the form, the cost of linear regression, the logistic regression, and now we have this binary SVM, which is basically the side constraint looks the same. They both have this regularization term. And now we have essentially the sum of this max of 0 and this 1, which was the task loss, minus the same exact form. And really, I want to emphasize the form here. So this is a linear function in weights, linear function in weights, linear function in weights. Okay, so it still has that, but it's different objective functions. Why am I doing this? Is because we're going to get to deep nets and show you a similar form and show you that these are all special cases of deep nets. And that diagram you have seen. Okay, one last thing before we move on from binary classification. It's possible to combine the log and hinge loss. As a reminder, log loss is the one that corresponds to logistic regression. Hinge loss is the one that corresponds to support vector machines, SVMs. And the way we can combine them is by essentially looking at the limit of this log of 1 plus exponential of minus f, remember what f was, over epsilon. And notice that if f is positive, this simplifies because essentially we end up with, in the limit, this gets large. This is negative. This goes to 0, becomes log of 1, which is 0. Okay? But for the case where f is negative, this is going to grow. It's exponential of number. It doesn't matter that this is getting small. So it becomes basically 0 times infinity in the limiting case, in which case you have to invoke L'Hopital's rule. And that's exactly what I'm showing you here. You perform that and you compute the limit, and you realize the limit becomes negative f. And in summary, basically what we have in the two cases, depending on what f is, you can just summarize these two conditions, that this limit is the max of 0 and negative f. Why is this relevant? Because you can now, I'll show you in the next slide, that support vector machine is what's known as the 0 temperature limit of logistic regression. If epsilon goes to 0 in the limit, you basically get the same thing as logistic regression. Okay, the two are the same. And here's the general form of binary classification. I'm writing in the form of that general expression that I have with the epsilon and log of 1 plus the exponential of L minus the same term, the f that we had before. And I won't, in the interest of time, I'll leave this for you to look at. But basically, look at the cases. If you set epsilon, okay, to 0 and L to 1, essentially you get this one and vice versa. So they're all related, okay? They're all related. They're all special cases of a more general formulation model. And what's shown here is that we can plug the same exact set of costs, but for different values of epsilon. And you can see as epsilon gets smaller and smaller, when we get to this color where epsilon is very small, this is starting to almost look like a hinge cost. So basically, you can see that a log cost, remember, was a logistic regression. So logistic regression starts to look like an SVM. Okay, so one last topic before we get to the crescendo, which is deep nets, is multi-class classification. I've talked about binary classification, but ultimately, if we want to go in the direction of functional approximation, we want to be able to do multi-class classifications. So not only is there a cat or a dog in the image, but let's say you have 100 different animals. Is it this animal? Is it that animal? Is it that animal? That sort of thing, or different classes that you have in the image. So what are the issues? I'm going to go a little fast and just capture the essence of some of the concepts. First of all, how would we perform that with the machinery that we have talked about for binary classification? Well, there are two ways you can think about that. The first one, which is referred to as one versus all, or one versus rest, which implies that we use K-1 classifiers, each solving a two-class problem. We have already an engine that does binary classification. Okay, so but we use K-1 classifiers. We just repeat the same method that we had. What does that mean? In this, for example, if these are, if you look at the classes, okay, so here, this line will decide us if this is class 1, that means that everything to the other side of the line is not class 1, which we can become class 2 or 3. The same thing over here. It's not class 2, and we declare that this is not class 2, not class 1, therefore class 3. Okay, but what happens in this region? So it doesn't give us a definitive answer for all possible data that we may see. Okay, so you can generalize this to a case where this actually, interestingly enough, goes back to the case of radio astronomy and arrays. You have, let's say you have K antennas and you want to correlate each antenna with all the other ones. How many correlations do you end up with? K times K-1 over 2. Or there is a table of K people and you raise your glass and you want to make sure that you cheers to every single one. How many of them do you have to actually, if you want to visit every glass? k times k minus 1 over 2. Okay, so that is basically the number of two-way classifiers, one for each possible pair of classes. And so it basically it classifies sample according to a majority vote. Okay, and what that looks like, of course, the issue is that two-way preferences are may not be transitive. Okay, in both directions. Okay, so how do we solve the problem given that there are these two limitations? The way we solve a multi-class problem, the way we formulate that multi-class problem is by essentially generalizing this idea to not a binomial underlying probability distribution, but to a multinomial probability distribution. And we explicitly write probability of the class being equal to one of any of the k possible classes, not just the binary, not just minus 1 and 1, but k, given the data. And this is the corresponding form of the exponential. And this is the term down here is normalization to just ensure that this is a probability. In other words, it integrates to 1. The probability density has to integrate to 1, probability mass function, and it has to be greater than or equal to 0. So that's this normalization guarantees that. And we maximize the likelihood as before. So they're very similar in the form. And so let me just show you an example to build intuition. Here we have, for example, three classes, phi1, phi2, phi3. Let's set phi3 equal to 1. And you can see that you're drawing lines, but these lines are not decision boundaries. You have to visualize that in this case, we have 3 dimensions. So these are actually planes, and you look at the intersection of planes. And what really matters is that at any given point in that 3-dimensional space, if you want to declare what class it is, which plane has the larger value in relation to the other ones. Okay, that's how you decide. And again, let me just go through these examples in the interest of time. You can look at the decision boundary, and of course, you can look at the probability function. As you can see, it's highest close to 1, and it falls off when you have this case. So you can do that. What happens when you have 2 classes? These lines, you may not be able to see that there are 2 lines, but these 2 lines essentially, or the 2 hyperplanes, or lines in higher dimensions, the lines coincide essentially. When you have a multi-class classifier, but you're using it for binary classification. That's what I'm referring to. Okay, let me skip through some details. The idea is that we can have a multi-class support vector machine very easily by just slightly changing the cost. Instead of having that original cost, essentially having a cost that looks like the following. We just basically do make a comparison between the yi's being the data point and yi's with respect to the class that we estimate with respect to the other ones. And you can write this in terms of an inner product. I'm going to skip a lot of these details because the derivations, because I want to get to deep nets. Since it's a topic that's going to be used in the subsequent lectures, I want to make sure that we have an understanding of those. But essentially, the machinery is the same. The only thing that happens is that now we write these weights as a set of k weights, this vector. So we have the mappings, and then we have this inner product, which essentially is like an indicator function that picks class 1 on top, the next class, the next class. It lines up all the k classes in here. And the equivalent formulation is very similar to what you saw before, except that now we have this essentially the difference in the 2 inner products. Notice there's this is a term that has to do with our labeled data, and this is a term that has to do with the class that we declare, and we want to maximize that cost. Okay, so let me just briefly show you. We have the same exact cost as we had before with the slack variables, and this is greater than or equal to 0, as we saw exactly in the previous case. And I can write it in this fashion. And then finally, I can write it in the form where I have the term known as the loss augmented inference, because this is the term that has to do with the class that we declare as one of the k different classes. Okay. How does multi-class SVM relate to multi-class logistic regression? It's essentially, again, going back to the same temperature argument in the last lecture. The two are related. One is a special case of the other one. Okay. The final point, without going through the details that I want to make, is that there are issues, as we saw, with models such as support vector machines. The main issue is that it still is limited by the linearity in the feature space. Okay, so it's still limited by linearity in feature space, and the way people who really worked, SVMs were, I would say, quite prevalent for several decades, even before machine learning was referred to as a discipline. Machine learning for problems of classification maybe up to 10 years ago. And the way people got around this inherent linearity in the model is by using something known as kernels. So in other words, instead of just specifically defining features, these functions of your data, you look for functions with certain properties that allows you to capture this inherent nonlinearity. So I'm going to skip over those details, except that I want you to be aware of the fact that it's possible to do, essentially, the idea is to replace the inner product with call to kernels. And the advantage is that we don't need to explicitly construct feature vectors. But we need to ensure that the functions that we call, these functions, are valid kernel. That means that it corresponds to an inner product in some feature space. And of course, there's some ways of guaranteeing that. You can check for something being a proper inner product. And there are some examples of kernels that one can use. I'm going to skip through all of these to get to the final topic for the remainder 15 minutes that we have. Okay. Deep neural networks. Why is it that, by the way, there's a good book by Goodfellow on deep learning. You can look at these chapters. What I want to do is a few things. One, I want to show you what the idea behind it is. And the take-home message is that they are just a generalization, a more, I would say, a more complex model for performing the exact same tasks that we talked before. And in fact, you can show that everything that we have seen so far, logistic regression, SVMs, are just special classes of deep nets. Okay. And of course, the machinery for why they work and how they work, of course, the subsequent speakers and also we will see in the coming days, both the remaining 2 days that we have, that there are architectural considerations, how you build these things, and the trade-offs to be made to do the function approximation. We're going to talk about all those, but at the beginning, I just want to make sure that we understand in what way they can perform classification of potentially large number of classes in higher dimensions, in what way they can accomplish that. And secondly, how the computation engine, how it works through essentially a forward and a backward pass, and known as backpropagation, meaning that application of subsequent chain rules. Let me just briefly show you that in our current model that we have, okay, there is a possible issue and limitation that I just talked about, which is linearity in feature space. We fixed that using kernels, but still, we are learning a model that's linear in parameters W, as you can see in this expression over here. Okay, and the idea behind deep nets is to replace this product of this linear product of essentially feature space with the weight. Just why not just write it as a general function, call that f of all three variables, the weights, the data, and the label. Okay, make this more general, and replacing this linear function with a more general function, and then everything else, if you replace it in the derivation of all of the models and the costs that we have, it essentially is the same. So the natural question is, what sort of function? What should that capital F be? Okay. What should, now that we have replaced this as a function, a general function, not just a linear product, what should that function F be? Well, it should have certain desirable attributes. What's the first one, if anyone has experience with it? I kind of alluded to the fact that we want to be able to, we still have to perform an optimization, right? We're solving for the parameters, okay? So that means that we have to be able to perform optimization. In order to be able to perform optimization, we have to be able to work with gradients, okay? So we want f to be differentiable. That's the first thing. The second thing is that we want it to be in a particular form that corresponds essentially to an acyclic graph, okay, with essentially in the form of a differentiable but also composite functions, so that the general function has the graph structure, something that's known as a computation graph. And I'll show you an example of what that looks like. So for example, if we have these nodes are weights, data and functions, and we have this composite structure, so that, for example, you can see F3, weight 2, building up this function, and that building the previous function. And this is really the computation graph is the internal representation used by DeepNet packages. And the reason why we want to do that is because we want to be able to do a forward pass and then just have an index of all the different classes, okay? And then be able to essentially go through a backward pass through successive applications of chain rule to be able to perform the optimization efficiently using this structure. But briefly, I want to show you so that we can really look a little bit in detail and develop some conceptual insight into why this sort of model should work, should, remember, to give us what our desired task was, to be able to do classification and generalize it to function approximation, okay? So this is what I'm going to spend maybe a few minutes on. Let's look at the underlying functions that are used in deep nets. So these are some examples. This corresponds to a sine. Sigmoid were used for a while. This is what's used frequently, which is known as a rectifier linear unit or a ReLU, and a variation of that that avoids this discontinuity at the origin. But these are examples, okay? So this is what examples of essentially this sigma that I'm defining, which is the function at each node. So how is that used? This is just a single node. You have a vector input. These are the data, x1, x2. Each one of them has a weighting similar to where I started. Remember, just W multiplying the data. You add all of these up, and what you end up with is essentially just a linear function, right? A linear function. Sigma, remember, is one of those essentially nonlinear functions that we talked about, like a sigmoid or a ReLU. And you have a linear function, that's the argument of that. This is just a short note representation. Its summation is hidden, but that's essentially what we have there. So what does that do for us? Let's look at it. So bias B is important. Remember what we had here. This is the model, what we have. That's the model of a line, right? Just like we had with SVM and all of the earlier models for classification, binary classification that we had. So if you look at the product W2, W transpose X greater than or equal to B, that means, just like essentially, look at this. This is the line W transpose X plus B equal to 0. So if this is greater than B, you're greater than that bias term, then we can declare that it's class, we output class +1. And if it's less than B, we output class -1. So essentially, establish the same exact thing, except that now a multi-layer, when we have these composite functions and we connect them in some fashion, this multi-layer neural networks allows us to divide high-dimensional space in a less complicated way and approximate functions. And approximate functions by mapping inputs and outputs of a neural net, okay, layered neural nets. Because essentially, this is just I'm showing just the line example of that. You go to higher dimensions, it's a plane. You go to higher dimensions, you have hyperplanes that are essentially partitioning that higher dimensional space, okay? So then what do you do with that? So that was just one node. You connect the nodes to subsequent layers. Each one of these is layers until you have the final layer. And this connection essentially allows you to essentially propagate weights as well as biases. And those are the quantities that you solve for computationally, okay, in order to essentially fit your deep net so that you capture the inherent input-output relationship without solving for that system in the middle that I talked about last time. You just learn that connection between the output and output by just essentially approximating the function that connects the input and output. So a few points. Number of neurons in each layer can be different. All weights on each connecting layers m-1 and m are, you can write it, capture it in a matrix form. And you can call the inputs and outputs in the way that I've shown over here. And this can be written compactly in the form. This is just for one of them. And you can just similarly just write the same expression for all of the nodes, connecting the nodes until the very last node, the output of the deep net. Okay. And what is it that we want? We want the output of the neural net to approximate some desired function. So this call this y hat being the output of the last, what the node output to be approximate a function. This is where I'm getting about finally to function approximation. Approximate the function f of x equal to y. So how is the function approximated? We use the labeled training data, inputs for which we know the correct outputs, even though f is unknown. We don't know the function, but we just know through labeling process that this input corresponds to that output when we have a set of those training data. And we minimize the empirical loss on training data, and that loss, again, it can be our choice, but we're minimizing that until our approximation, essentially we are setting the approximation of the class that, or the function that we are defining to be the output layer of the net. Okay, the forward feed is, if it's a scalar, for example, we can write that L to just be a distance between, Euclidean distance between the two. J, or the cost function, is a function of the weights and the bias. So we have to fit those two parameters, okay? And we want to minimize J, for example, using a gradient descent procedure. In practice, a lot of times, you may use a variation of the standard gradient descent known as stochastic gradient descent, in which case, instead of just going through systematic search of the function values, you may use some Monte Carlo sampling strategies to perform your optimization more efficiently. Okay, so we can compute the gradient for each term separately with partial derivatives. So in other words, we need partial of the L with respect to the weights, partial with respect to the bias terms. And again, in the interest of time, I'm going to skip through the details of the derivation. But if you go through it once, you'll essentially appreciate the fact that this is nothing other than application of successive chain rules, where you start from the last layer. This is the back propagation, the backward pass. You start from the last layer, relate that partial to the previous layer, and then you relate that previous layer to the previous one, just like that computation graph that we had, until you have a recursive relationship for essentially computing all of these partials using successive applications of chain rule. And you do that for both the weights and the bias terms. You can see that here, the weights and the bias. And if you just apply this successive application, you end up with this is the derivation for the weight. You can do a similar thing for the bias terms. And the summary is that you compute this for all I and for all layers. This is a number of layers all the way to the first layer. You essentially just perform this operation. And anyway, so the specifics of that you can just go through. If you do it once, it's very instructive. So if you want to use this, I recommend. Of course, there are packages for performing all of these, but it's useful to just see that. A few points. I want to take maybe 5 more minutes just to say a few things on topics that are coming up, just to set the background for those topics. What are the individual functions? I already talked about, for example, a fully connected layer. Convolutions. I think we need to cover that because we're going to talk about that, right? So I know that because we coordinated. So I'll show you exactly what we mean by convolutional neural nets. Rectified linear unit, we talked about that. So it's essentially max of 0x, maximum average pooling, soft max layer. These are all terms that at this point, the details of them don't matter because there is an art to being able to make sure that you are essentially utilizing these architectures in their optimum performance. So dropout, for example, means that you don't use some of the nodes. It's a subset of them, and you do that for various reasons. There's a batch norm. That's another one I've not listed here. You guys probably know about, use all of these. Okay, but I want to show you an example. This is actually a convolutional neural network. And this, what I want to show you this is because it's one of the early architectures. It's an architecture that was proposed by Yann LeCun. Some of you who have followed its developments may know that he was one of the people who won the Turing Award for this work. Okay, so he named it Lunette. The year is a long time ago, 1998. And the idea is the following. You have, this was applied, for example, in these images. And this is what's known as a convolution layer. First of all, notice something that's written over here: decreasing spatial resolution and increasing number of channels. When you go from here, you have 4 channels. And these channels are essentially, in this particular multi-layer perceptron, corresponded to subsampling layers, or what these days people can think of as max pooling. You just pick the max of something that you have computed in terms of your convolution. But what's the convolution? We already saw convolution yesterday. You have, in this case, you have a 2-dimensional kernel, maybe a 3x3 pixel kernel, and you move that around your image. You essentially compute the convolution, discrete convolution. It's just a sum instead of an integral. And you obtain with different filters. So this one may have a 3x3 filter. The other one may have a 5x5 filter. You end up with essentially multiple channels from that original image. And what that allows you is that you have now a more diverse set of features of that original image. Okay? And then in this case, it passes the 4 over here. This is 4 feature maps, but then it increases it to 6. Okay? And then performs another convolution. That's another convolution layer. And then another subsampling or max pooling. And then finally, it gets to this, the case where you have this fully connected, the last stage, to the output of the neural net. And let me ask you this question. How many classes was Yann LeCun trying to solve in this using the classification problem? Sometimes it's obvious because the final layer may not be a scalar. Notice in this case, there's the 1 node, right? Sometimes, you can have 1,000. In fact, AlexNet, some of you know, that also received some attention in that community because of its performance. I don't think it's named after you, Alex, but it's another Alex. It has, for example, at the output 1,000 nodes. But essentially, you can guess that it's either binary class. You can't tell from this picture. It's either binary classification at this last node or maybe 4 classes at the node right before that. Okay. Anyway, this is an example. Here's another deep net showing the same type of idea, which is structure is simple in that layer's output is used as the input for the next layer. This is an example of a fully connected layer, which I use to show you the machinery for backpropagation. Okay. So what are the trainable parameters in this? The W's are essentially these biases and that matrix. But of course, there's an issue with this fully connected layer. And suppose that the input of an image is a 256 by 256 number of pixels. Okay. And suppose that the output of the layer has identical size. And then we have the number of weights that are necessary is too large if you have these types of fully connected layer. And for that reason, there are many schemes for essentially bypassing that. There are many, many schemes, but just be aware of that. This shows convolution, the task of convolution. So you have a mask, and you perform the convolution, you get the results. The trainable parameters, as I alluded to, are the filter width, height, depth, number, and of course the bias is another parameter that you solve for. Maximum or average pooling, which is similar to that subsampling problem that I talked about. That, for example, that subsampling becomes very important in an application known as super resolution that tomorrow, right, Andres is going to talk about in the, what's that? Monday, not tomorrow. No, yeah, I've been giving back to back. I'm thinking, okay, the third one is coming up tomorrow, but Monday. Okay, softmax layer, which essentially is similar to just getting the values between 0 and 1 and probability. These don't have any trainable parameters, so that's why the dropout layer, that's why they're used in practice for that desirable property. I'm going to skip the summary that we saw. The final thing is that what's the cost? It's something known as essentially cross entropy, or also negative of log likelihood that we've been talking about. And I mentioned already that stochastic gradient descent is typically used. There are variations on how to speed this up. Momentum is one idea. It goes back to what you talked about yesterday, essentially overshooting intentionally in your search. Okay. I think I can skip the details. I already went through this backpropagation example. And the final thing that I want to say, I want to part you with, is that this f, the general function, is no longer constrained in any way. So what that implies, of course, it gives us this diversity of the ability to model general dependencies in a nonlinear or general fashion, but the loss function is generally no longer convex, okay? And if the loss function is not convex, from theory of optimization, we know that we have sensitivities to initial conditions, to where you start your iterations in your gradient descent or stochastic gradient descent. Okay, so we are also no longer guaranteed to find the global optimum. Part of the reason why it's important to develop some skill, some experience with working with these things to really understand, are we getting close to somewhere that's hopefully close to the minimum, the desirable minimum. And of course, initialization I already talked about. Okay, final summaries. A deep net with a single fully connected layer is equivalent to logistic regression. That's the take-home message of the reason why I showed you the development in the form of that general cost, okay? The connection between all of these. Because why am I saying this? Because you see sometimes papers in applied domains where people, instead of developing the appropriate model for the problem, they go through a list of, okay, I'm going to do a logistic regression, I'm going to do an SVM, I'm going to do a kernel SVM, I'm going to do a CNN, I'm going to compare the results. That's okay to do as a learning exercise, but it's important to understand that what we are doing a lot of times are basically looking at special cases of another more general case, okay? Okay, the deep nets automatically learn feature space transformations because of this hierarchical abstractions of data, such that data is easily separable at the output. Disadvantage of deep nets, we should always, not be evangelical and praise things. It's important to tell the whole story. The disadvantages is that they are computationally demanding, but of course, these days, there's a lot of advancement in using GPUs and in combination with other hardware acceleration architectures and ideas, and they require significant amount of training data. Those are the two things to keep in mind. Okay, why this recent popularity? By recent, I mean a decade, because now we have sufficient computational resources. If we are not sensitive about the power consumption, that's another thing that there are discussions on, of these large computational engines. We have more data, we have more advanced algorithms, and most importantly, we can't argue with something that works, even if we don't fully understand it. Okay, and let me just stop right there. I think yeah, I can go ahead and ask questions. I think Nick gave up on us in moderating the questions and answers because I went over by.
So
Yes.
I'm not going to ask a direct question about this. If I give ChatGPT a text in this context, how it corrects it?
Corrects it?
Yeah, it's a wrong text.
Okay. So GPT, in general, the G in GPT corresponds to a topic that we'll talk about tomorrow, generative models. So The idea behind that, remember, I started by saying that you either have labeled data, you have X, Y pairs, or you just have X, in this case, X going in there, except that the training has happened, the underlying idea behind that. The underlying idea is that there is an inherent implicit distribution that generates all possible text, okay, in large language models. And the goal of generative model is to somehow learn that distribution or approximate it in the best possible way. Once you learn the distribution of something, okay, then what you can do is you can generate new examples, but what you're talking about, I think, is slightly different variation of that, is the correction. So example, text correction. For text correction, a lot of that has to do with something known as structured learning. So for example, if you take advantage of the existing correlations. And by the way, what I'm telling you is a simplified version of the story, because there are many algorithmic innovations that work together to perform the task that you're talking about. But structured learning implies that suppose you have 4 letters and you want to predict what that word is, okay? And suppose that it's Q, okay? And it like handwritten text. Let's just slightly change your question. You have handwritten text and you want to do automatic hand recognition. There are 4 letters. You have Q, and suppose that this one is not really, we can't read it so well. Yeah, Q, I, T, right? And this, it looks like it's a V. So from just looking at the pixels, it could be U, it could be a V, right? But you can look at the fact that the correlations between the next letter to a Q, it's much higher for it to be a U than a V. And so it captures that structure that exists in trained data. But ChatGPT primarily works on learning the underlying distribution and generating things based on that distribution. That might be a correction on what you give it, because it has learned what the underlying distribution generating those semantics, syntax, and many other things might be. Would you guys like to add anything to that question? Okay.
I have a question. I have 2 questions. Could you just re-explain what it means for forward propagation and backward propagation in this context?
Yes. So the forward propagation, forward pass, is basically a model of how the layers, the nodes, so you have nodes in each layer, and with those nodes you have parameters, typically weights and bias, and how that is connected to the next layer and all the way to the last layer. So if you remember that computation graph that I talked about, it's essentially the functional dependence. What is the form of that composite function that starts from the first function and is a function of the subsequent functions? So just building that connection, that graph, essentially, that's the forward pass. How are they connected, okay? But now you have that connection, but you want to perform a different task. You want to perform a minimization. You want to find the parameters, either the weights, biases, or whatever, however you parameterize it. You want to find the optimum value of those parameters, given some objective, and typically it's empirical, what's known as empirical risk minimization. So you want to minimize the output of the last layer compared to, let's a desirable Y with all of the classes. The way you need to do that is you need to obtain the gradients, okay, so that you can essentially find the minimum of your function. To compute the gradients, that's the back propagation step. And what that means is that you essentially find the partials for the parameters, what they are at the final output of the deep net, and then you connect those partials based on the connection that you already established between the one before last to the last layer, and then you propagate it all the way to the very first function, F1. And you do that, as I mentioned, because there's essentially a recursive element in successive applications of the chain rule, because you have these partials that you have to compute. I mean, you don't do that those of you who do this, this is all of the solvers are there, but I'm just conceptually describing it to you. But that's back propagation. So that's the forward is connecting, building the computation graph. Back propagation is to solve that optimization problem to find the optimum parameters.
And then so for the labeling of the data set, if there's one thing to do it manually, but if you are also doing that with some sort of computation, then is like the bias that you introduce to your labeling kind of propagate through all of this as well? And how does it get captured, or does it?
Well, the assumption of being able to learn a function based on observing its input and output is that whatever input and output relationship you give it is what is basically established by the intermediate function. The function operates on the set of inputs and it generates the outputs. Now, if you give it a relationship doesn't represent nature or reality, it will learn a function that will essentially capture your whatever deviations from the mistakes in your labeling produces that. Are there methods of probably coming up with robust methods of capturing that? Absolutely. You can imagine that this is a very crowded and active field, and people work on all sorts of issues in terms of robustness of how to work with not only that, but how to generate even the labeled data automatically. Right. There are variations on the theme as much as you can possibly imagine. Semi-supervised, all kinds of different schemes. If you have partial information, but you are able to perhaps extrapolate on your training data, on your labels. How do you do that? And in fact, ideas even for using generative models to address some of the questions that you asked.
Thank you. I actually have some general questions. So how does a classification algorithm, a discriminative algorithm compares with something like a knife base in terms of inference, which is better?
What based? Can you repeat?
Knife base theorem, knife base algorithm in generative models.
I'm not sure if I
Okay.
follow or maybe are there other people who might have?
Knife base. Knife. Okay.
Can you elaborate on maybe you can help us?
It exploits the Bayes theorem
Uh-huh.
To do classification. It's a kind of a generative model.
Okay. I think I know what you're referring to. So one of the important applications of generative models, which I'm not going to go into those details, but for example, in inverse problems, which was a topic yesterday, and image reconstruction, processing, all of those, a lot of them are based on a Bayesian formulation where you have a prior. That's what we saw yesterday. A big role of generative models is to learn the prior. Remember, in fact, you asked the question yesterday, how do you choose the prior? What sort of priors make sense, right? We talked about priors that have some mathematical interpretation, such as smoothness, maybe total variation, maybe a sparse solution. We talked about those. But of course, you can generalize that by essentially whatever constraint makes sense in the context of your problem. The statistical formulation of that prior is typically how do you find your prior? In a Bayesian setting, what's the idea of Bayesian estimation? The idea is that if you know something about the underlying distribution of the unknown quantity you want to estimate, you will be able to do better than maximum likelihood. You would be able to come up with a more accurate and robust solution as long as you can trust that prior. So now generative models are used a lot for learning that prior because it goes back to learning a distribution, an underlying distribution. And of course, there's always a question of how much can you trust the distribution that you learn, and how do you know that that prior information that's supposed to constrain the solution space you search for is not going to actually bring you closer to bias. And so again, if you're talking about a method that purely uses a Bayesian estimation framework, I would say that generative models can actually work together, not in terms of a comparison, but they actually are used for learning the prior in a Bayesian estimation framework.
And correct me if I'm wrong, I guess all the discriminative algorithm that you have shown has a convex loss function. Are there discriminative models which has non-convex loss function like neural networks?
Yeah, I thought that maybe I went over that quickly, but in neural networks, we are not guaranteed convexity. So, and that's the reason why initializations become important.
Okay.
If a function is convex, your solution is independent of your initialization. You can show that result. It is dependent on the learning rate, the step size, but not initialization. But if you are not guaranteed convexity, then you're not two things. One is a question of local versus global minimum. You're not guaranteed global minimum. And also what you're saying, which is basically initialization becomes important. So there's a lot of, in fact, techniques for trying to come up with good initializations to guarantee that you don't stuck in some local minimum that's far from the true global minimum.
And a more philosophical question, just last question. Since I come from a field of like my previous work was in gravity, so it just struck my mind. Are there algorithms where they try to, for optimization, they try to look for maybe a geodesic in a Riemannian manifold, like on a sphere or something like that?
For doing the optimization,
Yeah,
performing
for
the optimization?
optimization.
I believe, but I wouldn't be able to tell you exactly what the approaches are to look for Riemannian manifold. They're doing a search on that. But I'm aware,
Okay,
meaning
yeah.
that I do see talks and papers on that topic.
Okay.
So yeah, optimization is a very rich field because first of all, it's older than many of these other fields. But it's also, it has had a renaissance because of machine learning, because it's really at the heart of machine learning. So yes, the answer is that I have seen those.
Okay, thank you.